It's time for section 2.5, continuity. Yes! Okie dokie. Continuity is going to be talked about in three parts. The necessary conditions for continuity, continuity from the right and the left, and properties of continuity. Let's go. All right, the first part, necessary conditions for continuity. Let's take a look at this. So let's just kind of look at a couple of different scenarios and see what we figure out about continuity. A good way to think about continuity is it possible to draw the following graphs without lifting the pencil from the paper, i.e. continuously? So let's take a look at this function. Here's a picture of this function if I were to graph it. Can I graph this function without lifting my pencil? No, I really can't. And in fact, specifically, the domain of this graph is that x can't equal 1. Okay? So the first conclusion for continuity is that f of x must be defined, okay, at a. Specifically, that a needs to be a part of the domain of f. Let's look at the next condition. Consider this piecewise function. Here we have x squared minus 2 until we get to 1, and then after 1 we have the graph of x. What is the domain of this graph and of this function? Well, if you look at it, all the x values are covered. So this has a domain of all real numbers, or we can write it from as an interval from negative infinity to infinity. So the second necessary condition for a function to be continuous at a point is that the limit has to exist. So notice, does this limit exist for this point here? Yeah, they don't touch. I still have to lift my pencil or lift my pen to draw this entire graph. Even though the domain is all real numbers, I still have a hole or a gap in my graph. So in other words, my left hand and right hand limits need to be the same. So let's look at this third condition. Again, we have a piecewise function. This one's just a little bit different. If we graph it, we can see that again, the domain is still all real numbers. But if I were to draw this graph, I still have to pick up my pencil in order to draw the entire thing. I can't just draw it without lifting my pencil. So this is not a continuous function either. So my third condition is that a function's got to be continuous at a point as long as the limit from the left and the right equal that point. So this gives us our definition for continuity, and we can look at it in three pieces. So a function is continuous at x equals a as long as the limit of f of x as x approaches a is equal to f of a. So in other words, all of this right here satisfies these three conditions. And by the way, these are the three conditions we need to show and prove every time we're demonstrating continuity. So make sure you show all three. Okay, the first one, f of x is defined for a, and a is an element of the domain of f. The next condition, the limit of f of x as x approaches a exists. In other words, the left-hand limit equals the right-hand limit. You got to show that. Number two, you got to show the left-hand limit and the right-hand limit and show that they're the same. And then the third step is that what you have in the first one and what you have in the second one are equal to each other. In other words, the limit of f of x as x approaches a is equal to f of a. So 1, 2, 3 steps we need to do for every problem. Let's take a look at an example. It says determine whether or not each of the following is continuous at the given point. Okay, so the number that they're giving us is 1. For this piecewise function, we're really looking to see if it's going to be continuous at the handoff point. So let's see if it is. Our first thing we need to see is f of x defined at x equals a? Well, in this case, yes. A is 1, and at x equals 1, we have this. So this is definitely a yes. F of 1 equals 1. That's defined in that second column in the piecewise function. Next, we're going to look, does the limit as x approaches a of f of x exist? Well, let's see. Does it exist? We got to look at the left-hand side and the right-hand side. In this particular case, the left-hand side and the right-hand side are taken care of by this top function here, okay? So let's take a look at that. So we're going to do the limit as x approaches 1 for x squared minus x all over x squared minus 1. So right now, if we were to plug 1 in, we get 0 over 0. That's no good. So let's do some factoring. So I'm going to factor an x out of the top. And then for the denominator, I'm going to factor the difference of squares. Notice here, I can get my x minus 1s to cancel. Poof, poof, gone. And then I'm left with the limit as x approaches 1 of x over x plus 1. Now we can plug 1 back in again. So I'll plug in 1. I'm going to get 1 over 1 plus 1, and that will give me 1/2. Oh, interesting. Now notice, for my third step, it's basically this. Does number 1's result equal number 2's results? In other words, is f of a going to give me the limit as x approaches a of f of x? And in this case, nah. 1 is not the same as 1/2. So this is not continuous. Write my answer here. So this is a nope. This is not continuous. Okay? Specifically at a equals 1. Let's take a look at this problem. G of x is defined as x squared plus the square root of 7 minus x. And we're looking to see if it's continuous at a equals 4. So first thing, we have to look, is f of x defined at x equals a? Well, let's plug 4 in here. What do we get? We'd end up with 4 squared plus 7 minus 4, which is going to give me 3, which gives me the square root of 3. Okay, yeah, it doesn't give me anything that's undefined. It is defined, right? This is very clearly going to give me a value. So I'm going to end up with, this is g of 4, is equal to 16 plus the square root of 3. All right, now it's time to look to see if the limit of f of x exists. Let's take a gander at the value. Now this one, it's not too bad, because if we do the limit, mind you, we don't have to do any smoke and mirrors. Okay, the limit as x approaches 4 of x squared plus the root of 7 minus x is just going to be 16 plus the square root of 3. when we plug it in, it's not going to make it any different. So in this case, it's pretty easy to see that for my first step and for my second step, that this is also, or that this is also equal. This is also true. The first one does equal the second one, so yes, g of x is continuous at, not x, sorry, a equals 4. This next problem is a twist on continuity, but it is extremely important. And it's kind of fun. Okay, we want to know for this piecewise function what value of c is going to make this function continuous on the interval of all real numbers from -infinity to infinity. That may seem like a big deal, but keep this in mind. Right now, the only thing that we're having a question about is 4. Okay, from all the numbers forever and ever, amen, from -infinity to +infinity, we are just going to look at the handoff point for the piecewise function, which happens to be x equals 4. Now, why is that okay? Well, keep in mind, no matter what c is, because c is a number, this is a quadratic function, this is a linear function. Normally, the domain, okay, the domain of a linear and quadratic function is all real numbers. So right now, we only have to prove, in this case, that a is going to be 4. And that's what we're going to look for to make sure that it's continuous. So is f of x defined at x equals a? Well, yeah. It totally is. Notice the equal to is going to give me the second one. So it is defined. All right. So if I've got, for the second one, I've got 4 times c, which will give me 4c plus 20. Okay. So for some value, 4c equals 20 is my limit. Next is the second one. And this one's a kind of cool one. So what we're going to do is this. We're going to take the left-hand side. Now, the left-hand side is this first one because it's for all the numbers smaller than 4. So what we're going to do is we're going to take that top equation and we're going to plug in x equals 4 because that's my left-hand side. So x squared minus c squared is going to give me 4 squared minus c squared. So I'm going to end up with 16 minus c squared. Now that's my left-hand side, right? Now I want to set that equal to my right-hand side. And my right-hand side is this guy right here, the 4c plus 20. This is my right-hand side. And if my left-hand limit is the same as my right-hand limit, then I can discover what value of c will make that true. So let's go ahead and solve this for c. Take a look at what kind of equation this is. This is a quadratic equation. So when I have a quadratic equation and I need to solve it, my goal is always to set it equal to 0 and then solve it either by factoring or using a quadratic formula. In this particular case, this bad boy is factorable. So I just moved everything on this side over to this side, added c squared, subtracted 16, and I end up with 0 equals c squared plus 4c plus 4. Well, that is factorable. That factors into c plus 2 times c plus 2. Now, this is c plus 2 squared, but since they're the same at this time, since I'm not factoring and I'm solving it, what I'm going to do is just solve it. I'm going to take one of the factors since they're identical, and I'm going to say c plus 2 has got to equal to 0, got to be equal to 0, which means that c equals -2. All right, now, is that true? Is that true? Well, you've got a result, plug it in, see if that is true, and then graph this piecewise function and see if this is a continuous function for c being equal to -2. Okay, continuity is also something that we can express from the right to the left. So let's take a look at that concept. Continuity from the right and the left. We know that a function is continuous from the right if the limit as x approaches a from the right of f of x is equal to f of a. So in other words, if you were like to look at the graph, this would be kind of like this. It goes that, and then it's defined here from the right. Okay, so not defined here from the left, but defined here from the right. A function is continuous from the left if it's the opposite of that. Okay, from the left, you see that the limit from the left is equal to the value of f of a, and from the right, it's not. So let's take a look at an example of a function that isn't continuous everywhere, but is continuous from a particular direction. Looking at f of x, notice that this is a square root function. What are the rules for square roots? Yeah, that radicand, that inside of the function, needs to be greater than or equal to 0. So let's take that. Let's take your x plus 2, set it greater than or equal to 0, and solve for x correctly. Now, if I've got x is greater than or equal to -2, this means that the interval of -2 to infinity, -2 included, is the domain of f. So now that we've found the domain of the function, we now know where that function is continuous. So f of x is continuous on the interval of -2 to infinity, where -2 is included. Next, let's look at the properties of continuity. If I have two functions, f and g, and they're continuous at a, and c is a constant, then the following functions are also continuous at a. I can add those functions and they'll be continuous. I can subtract those functions and they'll be continuous. I can multiply a function by a constant and that will be continuous. I can multiply those two functions together and that will be continuous. I can also take their ratio as long as the denominator does not equal 0. And that's a little hard to see, but that's a not equal to 0. Also, I can take the composition of those functions, and those will be continuous at a. So keep in mind that if I am looking at polynomial functions or exponential functions, these are continuous everywhere, okay? They're continuous from -infinity to +infinity. They're continuous on all real numbers. But if I'm looking at a rational function or a root function, a trig function, an inverse trig function, or a logarithmic function, those bad boys are only continuous on their domains, okay? All right, so if you have a function that is that's a polynomial or an exponential, it's all real numbers. All the other stuff that has holes or issues with their domains, we have to find their domains, and on their domains, they're continuous. All right, got it? You don't have to memorize these, but you do have to have a good working knowledge of them.
All right, let's look at an example. First of all, let's take a peek at this function f of x and see what the domain of f is. The domain of f, well, if we look at the function, the 2x does not cause a problem, but this square root of 25 minus x squared, that's a problem. Remember, for even-powered radical functions, like a square root, the inside, or the thing that's called the radicand, must be greater than or equal to 0. So that means that 25 minus x squared must be greater than or equal to 0. So I'm going to solve that by factoring. And then I'm going to look at a little sign test. So right here, I've got x equals positive 5. That'll take me equal to 0. And here for this factor, x equals negative 5 will make me equal 0. If I look at this graph of the inside, if I look at the graph of the radicand, if I look at the graph specifically of 25 minus x squared, I see that this function is greater than or equal to 0 between the negative 5 and the positive 5. So this domain right here, the domain of this function, is all the x values in between negative 5 and 5. So we know, based off of our previous theorem, that the function is continuous on its domain, but the only thing that we haven't shown is the endpoints. So when we say that the function is continuous on its domain, in this particular case, it's a closed domain. So we have to show continuity for x equals negative 5 and then for x equals positive 5. So let's do that. First thing we're going to look is f of negative 5 defined. Well, yeah, if I plug negative 5 into this function, I'm going to get 2 times negative 5 plus the square root of 25 minus negative 5 squared. That will give me negative 10. So yeah, it's defined. 2. How about the limit as x approaches negative 5 of f of x? Does it exist? And yes, it does exist. In fact, this limit exists because I can just plug the function, I can plug in the negative 5. So this is also yep. And then thirdly, are number 1, number 2 the same? And that's a yep as well. Because f of negative 5 gives me the same value if I look at the limit as x approaches negative 5 of f of x, which is 10. So it is continuous at negative 5. If I look at the continuity for positive 5, the answer ends up being the same. Is f of 5 defined? Yes, it is. Specifically, it's positive 10. Next, does the limit as x approaches positive 5 exist? Yeah, it does. It's also positive 10. Oop, I'm going off my thing. So I'll just do a big, thick exclamation point. Why? Exclamation point. Yes, it exists. And then for number 3, this is also a yes. And then I'm going to draw it over here. This is the case where f of positive 5 is the same as the limit as x approaches positive 5 of f of x, which in this case is positive 10. All right, so it's definitely continuous. Oh, darn it, I'm seeing a mistake here. This was supposed to be negative 10. Okay, so it is continuous for each endpoint on this. Hope that helps.